In this exercise, the basic concepts of internal fixation with screws and plates will be shown and practiced. There are two main sections: screw technique and conventional plating. The objective is to develop an understanding of the principle of interfragmentary compression that provides absolute stability. The standard 6.5 mm cancellous screw with a thread of 6.5 mm diameter and the 4.5 mm Cortex screw with a thread of 4.5 mm diameter are used in these exercises. The 6.5 mm cancellous bone screw is available with a 16 mm thread, a 32 mm thread, or fully threaded. In this section, a 4.5 mm Cortex screw will be inserted to function as a position screw. The following instruments are required: the 3.2 mm drill bit, the 3.2 4.5 double drill guide, the depth gauge, the large hexagonal screwdriver, the 4.5 mm drill bit, and the countersink. The generic bone is fixed in the bone clamp. The 3.2 mm drill bit and the 3.2 drill sleeve are used to drill through both cortices perpendicular to the fracture plane. The depth gauge is used to determine the required screw length. The 4.5 mm Cortex screw is inserted. Compression between the screw head and the bone surface is obtained. Because the thread of the screw is engaged in both cortices, the fracture gap will not be closed or compressed. This screw is called a position screw. The mechanism is now illustrated. The gap will not close because the thread of the screw is engaged in both cortices. By overdrilling the neocortex, interfragmentary compression can be obtained. To achieve interfragmentary compression, the hole in the neocortex must allow axial gliding of the screw. This is obtained by overdrilling the neocortex with the 4.5 mm drill bit. This is called the lag screw technique. First, at the other end of the bone model, a glide hole is drilled using the 4.5 mm drill bit through the neocortex perpendicular to the fracture plane. The 3.2 drill guide is inserted into this hole to direct the 3.2 mm drill bit, which is used to drill the far cortex. This ensures that the 4.5 mm glide hole and 3.2 mm thread hole are aligned. Countersinking the hole in the neocortex reduces the prominence of the screw head, which is advantageous in areas with minimal soft tissue coverage. The depth gauge is used to determine the necessary screw length. A 4.5 mm Cortex screw is inserted. As soon as the screw head touches the bone, further tightening will lead to closure of the fracture gap and interfragmentary compression. The screw is removed and the bone model rotated. A lag screw is inserted as before, with the only difference being the orientation of the lag screw relative to the fracture plane. When the lag screw is not placed perpendicular to the fracture plane, shear forces develop. Shear forces can cause displacement of the fracture fragments, as is shown in this demonstration. A 6.5 mm cancellous bone screw is used to demonstrate interfragmentary compression of a medial tibial head fracture with a lag screw. The following instruments are required: the pointed reduction forceps, a 1.6 mm K-wire, the 3.2 mm drill bit, which has the same diameter as the core of the screw, the 6.5 3.2 double drill guide, the depth gauge, the 6.5 mm cancellous bone tap, which has the same diameter as the thread of the screw, the T-handle, and the large hexagonal screwdriver. The fragment is reduced and secured to the bone with the pointed reduction forceps. For preliminary fixation, a K-wire is inserted parallel to the joint, avoiding the previously planned position of the screw. The hole is drilled with the 3.2 mm drill bit and drill sleeve without penetrating the opposite cortex. The depth is measured. The neocortex is tapped with the 6.5 mm tap and sleeve. In young patients with good bone quality, the entire length of the hole should be tapped. A 6.5 mm cancellous bone screw with a short thread and a washer is inserted. In its final position, the entire threaded portion of the screw must lie beyond the fracture plane to achieve interfragmentary compression. The required compression is achieved by tightening the screw. With dense bone, a washer may not be required. The reduction forceps and the K-wire are removed. Depending on the fracture pattern, a second screw or a buttress plate may be needed. The first part of this exercise will show the LCP used as a standard dynamic compression plate. The unthreaded half of the combination hole, known as the dynamic compression unit, accommodates standard 4.5 mm screws used for axial compression. Wide angulation of the screws is possible. The cortex screws can be used to achieve dynamic compression of the fracture when inserted eccentrically. They also can be placed neutrally to fix the plate onto the bone. The threadless part of the combination hole always faces towards the end of the plate. The space between the two inner combination holes, where the threaded portions face each other, represents the center of the plate. Based on this symmetry, dynamic compression can be achieved from both sides of the plate. The following instruments are required: the bone holding forceps, the 3.2 mm drill bit, the 4.5 3.2 universal drill guide, the depth gauge, and the large hexagonal screwdriver. The 8-hole LCP is positioned on the intact bone, marking the site where the transverse osteotomy is to be cut with the oscillating saw. The plate is placed on the bone and secured with bone-holding forceps so that the center of the plate lies over the osteotomy. The plate is now fixed in place with one screw. To obtain dynamic compression of the fracture, the drill sleeve must be placed eccentrically against the smooth border of the combination hole, away from the fracture. The spring-loaded drill sleeve should not be pressed into the plate hole. The insert therefore remains flush with the outer sleeve. Alternatively, by pressing the drill guide down against the bone, it will be centered in the compression unit of the combination hole. In this neutral position, no additional movement or compression will result from screw insertion. The spring-loaded insert now protrudes from the outer sleeve. With the drill guide in the neutral position, a 3.2 mm hole is drilled through both cortices. The depth gauge is used to measure the required screw length. A 4.5 mm cortex screw is inserted and tightened. The second half of the bone is reduced and fixed to the plate with the bone-holding forceps. Without applying any pressure to the universal drill guide, a 3.2 mm eccentric hole is drilled. The depth gauge is used to determine the necessary screw length. The second screw is inserted and tightened. As the screw is advanced, the screw head contacts the smooth slope of the plate hole. The bone is moved axially, creating compression of the osteotomy. However, this compression occurs only beneath the plate in the near cortex. A slight opening of the osteotomy in the far cortex can be observed. Here, the point is illustrated. To begin, the screws and the plate are removed. The plate is then slightly overbent with the bending press. The same osteotomy is now fixed with the overbent plate and the screws. For optimal compression without loss of reduction, it is recommended to sequentially tighten the screws. The gap is now closed, and the bone is compressed over its entire cross-section. A stable and anatomically correct internal fixation has been achieved. In this exercise, the function of a compression plate in combination with a lag screw will be shown. A new bone with a simple oblique type A2 fracture and a black foam sheath to simulate the periosteum will be used in combination with the 8-hole LCP. The position of the plate is defined by the planned direction of the lag screw. Compression of the fracture will be obtained in the axial direction with the use of 2 eccentric screws and 1 interfragmentary lag screw. To prevent gliding along the oblique fracture plane, the fragment forming an open angle to the plate must first be fixed in place. The sharp edge of the second fragment will then be wedged in. Thus, an optimal axial compression of the fracture can be achieved. The plate is secured to the bone with the bone-holding forceps. A hole is drilled in the neutral position using the 3.2 mm drill bit and the universal drill guide. The depth gauge is used to determine the necessary screw length. The screw is inserted and tightened. The reduction is verified. To compress the fracture, the plate will be fixed to the other bone segment with an eccentrically placed screw. Using the universal drill guide and the 3.2 mm drill bit, a hole is drilled in the eccentric position. The depth gauge is used to determine the necessary screw length. The screw is inserted and tightened. Axial compression of the fracture is obtained. Again, a slight gap in the far cortex is seen, which widens when bending the whole construct. To improve the stability by compressing the oblique fracture, a lag screw will be inserted perpendicular to the fracture plane. The near cortex is drilled with the 4.5 mm drill bit and corresponding drill guide to create a glide hole. The 3.2 mm drill guide is inserted into the previously drilled hole, and a 3.2 mm thread hole is drilled through the far cortex. The screw length is determined with the depth gauge. The selected 4.5 mm cortex screw is inserted. Additional interfragmentary compression of the oblique fracture plane is produced by tightening the screw. Absolutely rigid fixation of the fracture has been achieved by preloading the construct, as well as producing friction at the fracture site. The fixation is completed with 2 additional 4.5 mm screws at either end of the plate. In this exercise, the use of an LCP-L plate as a buttress plate will be demonstrated. Intra-articular fractures are usually caused by shearing and bending forces. Often, fixation solely with lag screws cannot prevent secondary displacement in such poor quality bone. This displacement can be overcome with the application of a plate that serves as a buttress. The following instruments are required: the large pointed reduction forceps, the 1.6 mm diameter K-wires, the 3.2 mm diameter drill bit, the 4.5 3.2 universal drill guide, the depth gauge, the large hexagonal screwdriver, the 4.5 5.0 threaded drill sleeves, the 4.3 mm diameter drill bit, the screwdriver shaft, the 4 Nm torque limiting attachment, and the torque limiting screwdriver. A split wedge fracture of the lateral tibial plateau is reduced anatomically and held in place with the large pointed reduction forceps. A pre-contoured L plate is used as a buttress plate in this type B1 tibia plateau fracture. However, it may need additional contouring to the bone. Otherwise, it could either fail to buttress or it could cause a deformity when secured to the bone. Once the plate fits the contour of the bone exactly, it is securely fixed to the bone. 2 1.6 mm K-wires are inserted at 90 degrees through the plate to the fracture plane so as not to counteract any subsequent compression. It is best to start the fixation of the plate on the diaphyseal side. The plate is fixed to the bone with the screw in the neutral position in the usual manner. The depth gauge is used to determine the necessary screw length. To secure the split wedge fragment, a locking screw can be inserted. After drilling with the 4.3 mm drill bit, the depth is measured. The screw is inserted, and final tightened manually using the torque limiter. The second screw is inserted in the same manner. The most distal plate hole is filled with a 4.5 mm Cortex screw. The K-wires are removed. The third proximal plate hole is filled with the third locking screw. The reduction forceps is removed. The fit of the buttress plate is snug. Compression has made the fracture line almost invisible. You should now be able to explain the principle of interfragmentary compression providing absolute stability in terms of both screw and conventional plating technique.